kind of uniform gadget will come up with nice Galois representations if you have hypergeometric data to be defined over Q. And essentially what you're going to compute will be the HP function. However, the HP function itself, even though under the setting is going to be rational, it may not be integer. So you need something additional to make it up to the whole trees to be integer. And now I'm going to quickly kind of go over the Gross-Coplitz formula, because what I want will be introducing a step function. The Gross-Coplitz formula says that now if you consider the characters, it's going to be from the finite field. In this, I'm only telling you the version over FP. Now is to CP over here, instead of going to Q bar over here, going to CP over here. And if you pick a correct choice of the
CP star
primitive piece root. Sorry?
CP star multiplicative group.
Okay, yeah. So CP star over here, going to the multiplicative group. And if you're picking a correct, so the additive from, there is a Gauss sum, you use the correct additive character, and the multiplicative character, the generator, you use the Hypergeometric character. Then what you're going to attain, which is based on, in the background, there is it's the Gauss sum value is relating to the gamma function. So there will be this power pi p, it's a fixed root of x to the p minus 1 plus p to be 0 in CP. So the primitive piece root is chosen so that it's going to be congruent to 1 plus pi p modulo pi p squared. So if you're doing such a careful kind of patching, the result will be the Gauss sum. It's going to be, there is this more or less fractional power p, and then there is the p-adic gamma function. And what I want to concentrate for today will be how this power of p will be put together in the h function over here. So the h function, the construction using a bunch of Gauss sums on the top, and in the denominator, we're going to combine all the power of p all together to get to a step function. So if we plug this Gross-Coplitz formula into the definition of HQ function, we're going to get to a combined p power for the case term. So it's going to be graded by the Hypergeometric character raised to 0, 1, all the way to q. Here, I'm looking at p's case, p minus 2 power. And using this formula, there are contributions from here, here, and here, and here. So we're going to come up all together into a collective power. The collective power, if I'm doing a normalization for the k between 0 to p minus 2, if I'm doing the normalization to make it within the value 0 to 1, the collective power can be described by such a step function. This step function, the x value goes between 0 to 1 because of the normalization. The value I get is between 0 to less than 1. And the step function will jump up and down depending on whether I will hit those values, AI, or if I hit AI value, the graph will go up. If I hit 1 minus bj value, the graph will go down. And such a function is going to be well defined for p not dividing the least common denominator if alpha beta are defined over q, right? If alpha beta are defined over q, it's well defined. If alpha beta are not defined over q, the picture will also depend on which p you are using. The jump might be at a different place, but this is going to be uniform if alpha beta defined over q. And let me actually also compare the step function. I'm going to give you an example with the plot. Consists of root unities coming from AI and bj on the unit circle. Let me give you an example. This example over here, we have alpha consists of 1/5, 2/5, 3/5, and 4/5. And the beta value will be 1, 1, 1, 1. So the jump occurs at AI, and the down occurs to 1 minus bj, which will be 1. So I'm not going to worry about that over here. And also for the step function, the convention will be all the AI and bj are normalized. So we're taking the fractional part. The value will be lies between 0 and 1. Okay. And the step function we get to, and the collective power of p start with will be 0. Then it go up to 1, go up to 2, go up to 3, and go up to 4, right? And if we look at the corresponding plot for the location of the root unity according to alpha, it will be the first one, second one, third one, and the last one. And for the beta value, it corresponds to only this point up here. So more or less, this is the same picture, but it's better way to deal with the multiplicity. All right. So we get to this picture over here, then I see there are 4 steps. And if you still remember, this is corresponding to the Dwork family, which is the 5th one. And if you look at its mirror, what we talked about yesterday will be what happens to the mirror X3. It's actually the Hodge numbers will be 1, 1, 1, 1. All right, the Hodge number for this particular case will be 1, 1, 1, 1. So you have 0 and 101 and 0, etc. And I want you to kind of think about this 1, 1, 1, 1. You walk up the steps. 1, 1, 1, 1. You walk up the steps this way, right? And so this is actually the kind of the situation for the step function occurs to the Dwork, degree 5, the Dwork family's mirror. And another thing I should probably point out will be what's the kind of the height. The height here will be 4. Of course, I also have to tell you the low. The low here will be 0. So there will be a notion called the wave function. The wave function basically will be correlated to, if I'm going to get to modular form, what's the weight of the modular form? The wave function, if you have alpha, beta defined over Q, it only depends on alpha and beta. It will be the maximum of my step function subtracting the minimum of the wave function. In the previous example, the wave will be 4. All right, so we mentioned in the rigid case, one of the case for the quintic case, which is proved by checksum, you get to a wave 4 modular form, and level will be, in that case, it's 24. All right, so it's relating to the weight over here. There is also another adjusting factor. This adjusting factor actually accounts for the T-twist, right? In the formula, when we get to the BCM version, there's some power P that we need to do the normalization. And then there is also, in case the minimum goes to a negative number, there is also a correction term coming in. We will use that when we get to the Magma package. All right. So let's look at the next picture. If I have alpha to be 1/2, 1/2, 1, 6, 5, 6, beta to be 0, 0, 1, 2, 3. In this picture, if you look at the plot on the root unity, you start from 2 step here, and then you go to e to the 2 pi I times 1, 6. So this is from alpha. And then you come back to 1/3. So this is from beta. And then you have alpha here appearing twice with multiplicity 2. And then there is a beta and alpha. So it's actually using the step function, you can kind of stretching out the things a little bit, which is in the way easier to understand. So start from 0, it will first jump up to 1/6. So at 1/6, it has the first jump. And then when I get to 1 minus 2/3, I have the first down. And then I jump up because I hit 1/2 and 1/2. It jump up and down, etc. And for this particular case, if we compute the maximum, it will be 2, the minimum, 0, the weight, 2, and the adjusting factor, which is computed from two things. One is the minimum is 0, and it's also the length of alpha set, which is 4, and how many integers in beta, which is 2. So the adjusting factor will be -1 for this case down here. And another example, I want to show you that it can go down first. Okay. So in a similar picture, if you go to this picture, it starts from the first down will be when you hit to, actually, when you hit to 1 minus 5/6, which is 1/6, you get the first down. And then it will go up because of you hit 1/3. And then you go up, 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 up. You get to here, right? And then, so it go up again because you had 2/3. And then you go down because you hit 5, 6, etc. So in this picture, the maximum will be 5. The minimum is -1. And so when you're computing the adjusting factor, it's going to be negative of the minimum, which is 1. And another term, which is the Tetris term, is coming in. It's 6, which is the length. 4 will be 4 integers and dividing by 2. So I don't need any adjustment factor for this picture over here. And why I need that? Because I want to introduce how you play around with those kind of representations. There is a Magma package on hypergeometric motif implemented by Mark Watkins. So I only want to show you how it's related. We mentioned about the BCN Galois representation, which is for GQ. However, if you use what Mark Watkins implemented directly, he already done the normalization for you. That means he's always putting things up starting from here. You won't see this kind of behavior going down. So he moves things around, so it's a normalized version. That means if I use my BCN computing from each function, if I do a Tetris according to T, then I will get to what Magma tells me. And what he computed is more or less in the version of local zeta function. So he actually computing the inverse. So he's using the arithmetic Frobenius when he's doing the computation. Here's one example. If I'm looking at the Dwork degree 5, the Dwork family, so the parameters that I type in 1/5, 2/5, 3/5, 4/5, and then I type in 1, 1, 1, 1, or if you like, you can put 0, 0, 0. It doesn't quite matter. It will take the fractional part for you. And remember, in this case, it's wave 4. And the adjustment will be 0. I don't need any twist. Okay, let's compute at 1. At 1, there, as what Bill tells you, it's going to be, there is a one-dimension job because of the what happens to the local monogeometry at 1. So in this case, it's going to be 4. And there is a primitive part, which is 2-dimensional. There will be additional 1-dimensional representation. And in Magma's implementation, Mark directly forget about this guy. So he outputs for you this 2-dimensional representations behavior. So in this case, if I put in prime p to be 7, what you will get is 343, 7 to the 3 power. It's conjecturic. Conjecturic means it's 2-dimensional, right? And the absolute value of all the roots will be p to the 4 minus 1, 3 over 2. However, if you change your fiber, if you change lambda to -1, it's going to be the generic case. What you will get will be 4-dimensional. So for this case, it's 4-dimensional. And again, you can look at what's the corresponding absolute value is the correct absolute value as well. Okay. And I'll show you another example where you need the twist, because the absolute value we set up in the kind of Katz and BCM formulation, the absolute value is correlated to the length, which is 4. And then the absolute value is supposed to be on the primitive part is 4 minus 1 over 2, which is 3 over 2. In the cases when you use 1/2, 1/2, 1/6, which was the second example I showed you, the weight's only 2. That means after you're doing the adjustment factor, you take away 1, what you get to the absolute value becoming 1/2. If you put into Magma, again at 1, the representation decomposed into 2 plus 1, and Magma forgets about 1. So it tells you what happens to the two-dimensional representation, and the absolute value, as you can see, is going to be square root. It's a reciprocal of square root 5. And if you get to minus 1, it's 4-dimensional. All right. And then in this case, Magma also tells you you can also do the factorization into 2 pieces. So you can play around by using this Magma package. All right. So this is the previous few slices only tells you what you will get if you use Magma. And now, with this whole package coming up, you see all of a sudden there is a kind of uniform way to construct hypergeometric Galois representations. All you will need will be alpha, beta, and if alpha, beta turn out to be defined over Q, you can use Magma to do the numeric computation to verify what you want to compute, or you can do the implementation yourself. We did that, but it turned out our algorithm is not as fast as Mark Watkins' algorithm. Right? You can do the implementation yourself. That's no problem. So given alpha, beta defined over Q, or without the assumption defined over Q, and depending on which lambda you're going to choose, you're going to come up with a wide variety of Galois representations. And this is by the work of David Roberts, Fernando Rodriguez-Villegas, and Mark Watkins. They actually use this gadget to consider hypergeometric L functions and use those kind of as testing ground for standard conjectures on L functions. And by the general philosophy due to Leibniz, we all kind of trying to we hold to prove, or at least we believe those Galois representations are automorphic. All right. So because of the available techniques, so we'll kind of concentrate on what about degree 2 subrepresentations coming from hypergeometric data. Of course, the first candidate is alpha beta to be 2. So this is what I mentioned about my joint work with Fuselier, Ramakrishna, Swisher, and Tu. When you get to the alpha set to be length 3, you can still get some nice two-dimensional Galois representation, especially when it's self-due and you look at the special fiber lambda equals to 1. You will get very nice representations out from this setting over here. And you can do the same thing when the parameter set is going to be 4. And if it's self-due at lambda equals to 1, you can also get very nice Galois representations. I should mention, in this case over here, when alpha, beta are both 3, if both alpha, beta define over Q, a priori for generic lambda, it's going to be 3-dimensional. However, all such representations are coming from symmetric squares. So in the background, there is also 2-dimensional representations coming in, which is due to the Clausen formula. I will mention a moment later. Right. And towards the very end, I want to show you a recent result by Winnie Lee and my colleague Fanting Tu. We use a repose formula over finite fields, in which case the multi-set went up to length 6. And we consider well-posed series, self-dual, and again, the argument is 1. Okay, so there are some of the situations we know we're going to get in two-dimensional hypergeometric Galois representations. Any questions before I move on? All right. So I want to quickly mention about, now we have all the kind of a source of Galois representations. Here's the kind of the theory, how we can identify correctly if you get to the two-dimensional setting. And of course, now this is becoming a well-known technique in modularity lifting theorem. Okay. And so if you start with something which is two-dimensional, irreducible, odd representations for GQ over L-adic field, if you know it's motivic, so it's unramified almost everywhere, and then you know the behavior at decomposition group. For our cases, you can choose L, and then Katz already have the description for those decomposition groups individually. And if you know it's crystalline with H-tail weight 0R, and regarding the adjustment factor, is more or less I'm doing the adjustment factor to make sure a priori the representation I come up with may not have any H-tail weight 0, and the adjustment factor is to make one of them to be the minimal one to make it to be 0. And for the two-dimensional case, the conclusion will be then your representation will be modular. It will be corresponding to, if you look at the second way, it's a way, the second H-tail number will be R+1 holomorphic Hecker eigenforms. And when we look at the settings we are considering, in the cases when both alpha beta defined over Q, and if lambda is also defined over Q, the representations are not only two-dimensional, but also there is the one very nice thing, the coefficients are going to be integers for the situation if I have two-dimensional representation coming out from hypergeometric setting. And the back primes, you can control where they are. The very back prime occurs to P dividing the degree of the cyclotomic field. And there are also possibly back prime coming if they divides your fixed fiber, which is assumed to be now a rational number. If P divides either lambda or 1 minus lambda, or its reciprocals, then there are a finite of them considered to be possibly the back prime. And other than that, everything else will be good. Then you can use, this is the result by Sayre. It says, if you have an integral way holomorphic Hecker eigenform, and the key point is if the coefficients are all integers, then at the back prime, the exponents are controlled. It could be go up to A if P is 2. If P is 3, it can go up to 5. Otherwise, the power will be at most 2. So that actually tells us that once we have a fixed hypergeometric datum defined over Q, it becomes a finite search. All right. Especially with Mark Watkins kind of implementation, the search is pretty fast. So let's get back to Calabi-Yau threefolds over here. This is based on exactly what the idea outlined in the previous page. If we get back to rigid Calabi-Yau threefold at the end of lecture 2, we are actually considering the alpha set to be length 4, beta to be all ones. So the description will be, its alpha is self-dual, so it's R1, R2, and 1 minus R1, 1 minus R2. And Ri will be 1 over an integer Euler number to be 1 or 2. Or there are cases the Euler phi number could go up to 4. So for those cases, it's very much like the Dwork degree 5 family. The step function will be going up like this way. So indicates that the mirror also have that H3, the Hodge numbers will be of this sequence. And if we use Katz result, we know that for X3, a priori, there is a one-dimensional job. So it's going to be three-dimensional Galois representation. There will be a primitive part, and then there will be an additional part. And when lambda equals to 1, right? So when lambda equals to 1, this will happen. So using the strategy that I outlined in the previous few pages, in a joint work with, again, Fontaine, Noriko Yuri, and Wading Zudling, we are able to identify for each of the 14 cases, right? The representation can be written in terms of HP function now without any normalizing factor because they're all integers. And we identify the values for each good prime as long as it's bigger than 5. The value for the HP function is the same as the AP, the piece coefficient of a precise wave 4 Hacker eigenform. I will show you in the next page. Plus, the one-dimensional case has absolute value P, and then here everybody is generically the eigenvalue, the roots of the characteristic polynomial have the length to be p to the 3/2. So there is p, there is a slightly smaller. There is explicit, depending on which case. Of alpha, there is at most order 2 characters. So we identify them very explicitly. So some of the description are given by the eta function, but some of them gets too big, so I just keep a few which are easy to describe, but everything will be explicit. The label over here, we use the L function and modular from database, which is kind of useful. And here indicates they're all wave 4. The level could be 8 or 36, etc. The characters could be the trivial character, or it could be the character corresponding to the what's described in the subscript. Okay. So which is the modularity result? And then I'm going to get to the application tomorrow for this particular result. And I would like to also kind of mention now, if I consider either the normalized hypergeometric function over finite field or the period function as traces, then how can we understand classical formulas in such a formulation? Right, which will be what I'm trying to telling you in the next few slides. The first formula, which is actually a very useful formula, is called the Clausen formula. The Clausen formula says, it's one of the very rare situation. If you start from a 2f1 hypergeometric function, if you put the parameters in the following way, there is a c, which is a parameter. C also appear here, C minus S minus 1/2. So it's one of the formulation for Clausen. Then if you square this 2f1 function, you will get to 3f2. So it's one of the very rare octile formula, which will doing kind of square or product of 2f1 hypergeometric functions get to 3f2. In general, this will not happen too often. And what's in the background is actually, if you look at the Riemann scheme, what it tells you will be, you start from the local solution is 2-dimensional. So you have V, which is 2-dimensional. And if you're doing V tensor V, it's 4-dimensional. So it decomposes into symmetric square and the alternating square. which is 3 and 1 dimensional, it tells you that this guy is basically lies in the symmetric square of the solution space on the left-hand side. So Rod Evans and John Green gave the finite field analog purely in terms of character sums. And it actually explains things exactly in the same flavor, because what we consider here, the left-hand side is the chase of a two-dimensional representation for generic lambda. And now chase square means I'm computing the chase of the tensor product, all right? So what you get to is this part is the symmetric square. And this part down here is going to be the alternating square. And why there is additional kind of things coming in is, of course, the structure may degenerate when C is going to be the trivial character. All right. So there is a, let me see. Yeah, so things will degenerate. The delta term is always telling you things will look differently when you get to some degeneracy over here. So if you turn John Green's identity into this perspective, then in the background it's telling you what happens to a Galois representation. If you're doing the symmetric square, if you're doing the tensor product of this representation due to the symmetry, what you get to will be this three-dimensional representation plus a linear term. So everything's explicit. All right. And it's also became a fun for us to look through the classical formula and trying to understand what they mean in the Galois perspective. We dug out a lot of things. We find it to be really interesting. All right, this is one of them. All right. So now I would like to get to the Whipple's formula. The Whipple's formula says, for the 7f6 on the left-hand side, which is in primitive because the difference of the upper and lower is 1, it's an integer. It's well-posed means a plus 1 is a plus 1, and then if you add any other column, you get a plus 1. So it's well-posed. So it's a well-posed series at 1, all right? So how should I think about that in terms of Galois perspective? First, I forget about these two guys. They correspond to the same character. So it dropped down to 6f5, and it's at 1. Okay, then according to Katz, things has additional one-dimension drop. All right, so if I know it's going to be self-due, I know that it's going to be, the corresponding picture will be 5-dimensional because of the one-dimension drop. If I know that it's self-due, it's going to be, the primitive part will be 4, and then it's 4 plus 1. How about the right-hand side? There is a gamma factor. To save space, I dropped the gamma factor, which is corresponding to a one-dimensional Galois representation. I'm not going to worry about that right away. So let's concentrate on the 4f3. This case over here is not obvious whether it's primitive, but generically, if it is, it's 4f3 at 1. So again, if it's self-due, we know that 4 has a one-dimension drop, so it's a 2 plus 1. So what Whipple's formula, if I'm purely just in terms of Galois representation, it's kind of a funny formula relating something 4 plus 1 to something 2 plus 1. All right, so that's why the formula is kind of puzzling at the first sight why this could happen. Right? And actually the key point is because of the process. I dropped this too. Right? So let me move to the second page. The second page, I just say that now I want to create something which is self-due. Right? In order to create something self-due, we put the assumption C plus D to be 1 to make it self-due, and F plus G to be 1 to make it self-due. And I also want the denominator to be self-dual, right? So the denominator to be self-dual, the denominator essentially is 1 plus a minus ai. I do not have too many choices for a or for the to make it to be self-dual. More or less force me to choose a to be 1/2 and e to be 1/2. And then there is some of the kind of technicality over here. It's minus p over 2 is because the Whipple's formula, a priori, you need to make sure both hand signs terminates. That means I would need one of the parameter, the upper parameter, to be a negative integer. Otherwise, it's not going to state it in this way. There is a different formulation. All right, so I put the slight deformation over here to make sure this choice over here looks like 1/2 is going to be a negative number, so that both hand side terminates. All right, so but we're going to forget about that when we get to the hypergeometric motif. Putting things up together after I specialize a to be 1/2 and c and this value are different by the sum is going to be 1, etc. I get to the hypergeometric motif once I drop this 2. So the left-hand side, the hypergeometric motif, both hand sides evaluate at 1. The left-hand side, the parameters will be 1/2, c, 1 minus c, 1/2, f, 1 minus f. And down here, the lower parameters is 1, 3/2 minus c, 1/2 plus c. They are not exactly sum up to 1, but they sum up to an integer, so it's fine. They sum up to 2, which is an integer. And then you get to 1, you get to this 2 number, they sum up to integer 2 again, which is fine. And then on the right-hand side, the 4f3 also evaluate at 1. And the upper parameters, if I forget 1/2, I get to 1/2 f, 1 minus f. And then I get to 1, 1, 3/2 minus c, and 1/2 plus c. So again, it sum up to 2. So far, so good. That means I'm actually coming up with a pair of self-dual representations, both evaluated at 1. And the structure on the left-hand side is representation-wise is 4 plus 1, and the representation-wise is 2 plus 1. Okay? So then what we actually attain is as follows. If you let M again to be the LCD, all right, this time this is going to be the least common denominator of the HD, which is 4, length 4, and length 6 over here. There is an additional kind of integer coming in as least common denominators of something, which is very explicit. And these two numbers, either they are the same or they are at most different by a multiple of 2. And this LCD is coming in the background. And actually, there is a Clausen formula that we use. I won't have too much time to explain that. But the result is as follows. A priori, the representation, both of them will be for Gn. It could be bigger than the G capital N over here. Could be the same or could be index 2. But doesn't matter after you're doing the restriction to possibly an index 2 subgroup. What you will see will be your representation, which is 4 plus 1, decomposed further into 2 plus 2 plus 1. And one piece of them is the same as the one coming from the representation on the right-hand side, so which is 2 plus 1. But you need a tail twist. After the tail twist, so this stands for the cyclotomic character, correspond to the LAD field. After you're doing the tail twist, it will be exactly one piece out of the big representation on the left-hand side. Plus, actually, the most interesting part has been filtered in the process. It's going to be something two-dimensional, which is actually the key part coming out from in the process, again, because we use a special product structure this part is coming from a symmetric square, and this part is coming from alternating square. So we put up things together in a formulation that, if you look at Whipple's formula, I cannot write it down in terms of character sum, but it makes perfect sense in terms of Galois representation. That means, unlike the case as John Green and Ron Evans and Green, they did that. Character sum version is very parallel. But for this case, you do have to explain the situation in terms of Galois representations. Once you see the Galois representation, if you drop this 5/4 and 1/4, then the correspondence will be the hypergeometric kind of representation on the big left-hand side. It's a bigger one. So it's going to be a priori 4 + 1 dimensional. It decomposes into one piece, which is this 2 + 1 representation, and the P corresponds to the Tate twist. So the P corresponds to the Tate twist, and you have this representation over here. They will agree as one factor, and the most important factor will be the remaining one that you are not seeing because of this process corresponding to more or less differential of second kind, not the first kind. All right. So I'm not going to go through the proof. I do have videos about more details listed on my website. If you're interested, feel free to take a look at that. Right. I gave another talk at Vanderbilt, and there is a recording there. Right. So more or less now, let's go to some cases. With that said, Whipple's formula gave us a convenient way to look for decomposable Galois representations. So what we did next step will be we putting up the parameter in the way so that both hypergeometric motifs are defined over Q. And there are 7 cases. And the first case, if I choose CF to be 1/2, what we see is the correct decomposition. So the correspond to the second hypergeometric motif, they're coming from a second power here. They all have a Tate twist, as you can see. And the major part will be this power here. It's actually correspond to the picture of the step function. Right. So if you want more details, please feel free to check out our paper. I would like to talk about some of the very quickly wrapping things up. Right. So this result, basically, as a character sum result, it was first conjectured by Koike, and it was for the first case first solved by Sharon Fischek, Keano, and Matt Papanikolaou. And Mortensen actually kind of conjectured, they mentioned in this paper, if you look at the truncated hypergeometric function, if you're doing the truncation, comparing to the piece coefficient of the target modular form, which is the major part over here, Eric Mortensen discovered, wow, they agree up to a power modulo p to the 5. And his conjecture kind of proved in part for the Mach 3 version was proved by Osborn, Rob Osborn, Armin Strauss, and Vadim Sudling. Right. So actually, after we done our case, we identified there is another modular form, which is the middle layer. I keep telling Winnie that we are looking at onions. there are 3 layers here. These are onions, 3 layers. You have the outer layer, you have the middle layer, you have the inner layer, or more like maybe avocado. So you can peel off the middle layer by using somehow Whipple's kind of formulation. And I would like to just mention that it's very kind of compatible. Everything's so compatible. If you go to the untruncated version, and then Fontaine and I able to verify that they are actually an explicit period on the modular form, right? So this is a computation looks kind of arbitrary. It's not, because these are transcendental numbers. It's very difficult to pin down them to be the same. It's totally non-trivial to claim that this transcendental number and that transcendental number turn out to be the same. So this is the Archimedean analog for the what we call the supercongruences that I will get to tomorrow. All right. I think that's the end of my lecture, and thank you. Thank you for staying to the end.
Let's thank Ling.
And then here I put the